Draw an energy diagram for the conformational analysis 360 degrees of propane. Label both axis and all minima and maxima of the energy diagram. Alright, I'm not going to be labeling the axes. You guys are going to have to remember that on your own. But let's talk about the conformational analysis of propane. So, our propane molecule looks just like that. 1, 2, 3 carbons. Now, when we're looking at propane, I want you guys to get out your molecular modeling kits. And, okay, I'm going to draw a little eye. Okay, that's not an eye. All right, here's our eyeball. Our eyeball is looking straight down that way. Now, when we're looking at our axis here, we're looking at one carbon. There's a carbon behind it that we can't see. And then carbon right here. And of course we have our hydrogens. And it's kind of like a peace sign. The angles aren't perfect, nor that. But then we're going to have our hydrogens in the back here as well. Now, this is our staggered position. Staggered position. Whereas if I draw that same molecule again, carbon in the middle, carbon behind that too, everyone, and then we get our carbon over here, and then we have our hydrogen here, but we can rotate that back carbon. It's not in a pi bond, so what we can do is, I'll put it in light blue here, is, oh look, that's a hydrogen. Excuse the plane going overhead, that's a hydrogen too. And oh, wow, another hydrogen. What do you know? There's 3 hydrogens on that carbon. So that is our eclipsed diagram of our conformational analysis. Now, to you, which one looks more stable? To me, the staggered one does. Why? Because there's no clashing. You know, hydrogens have mass, and it's all happy. Whereas in our eclipse, or I shouldn't have drawn over the carbon like that because carbon has its own hydrogens, everyone. If we look at the eclipse, we have our hydrogen mass here, and then, whoa, hydrogen mass there. Do you see that, this overlap here? Yeah, we don't want that. We don't want that, guys. So let's take a look at what's going on over here. So propane only has 3 carbons, which means there's 3 possible positions for the eclipse version, and there's 3 possible versions for the staggered position. So let's draw a little diagram of our staggered again. We have 3 possible positions for that carbon to be in. Our carbon could be here, our carbon could be here, and our carbon could be here. And let's say we're not rotating our hydrogens in the back. So, oh my gosh. So we could have it here, here, or here. That gives us 3 positions in our staggered version. And staggered is lower in energy because we are not getting that steric hindrance, right? And we're going to add our hydrogens there. So there's a little bit of steric hindrance going on. But there's really not much because it's hydrogens. And either one is going to be the most stable because it's all equal. So if we go down here, our lowest energy is our staggered position. See? Could be there, could be there, could be here, and could be back up there again. Meanwhile, our eclipse version, if I were to go ahead and draw another eclipse diagram, carbon in the middle, and there's a carbon behind that too, guys. Don't forget that second carbon. It's there. It really is there. We're literally looking at this. Okay. So we have three, oh my god, horrible peace sign, potential positions for our eclipse. So let me draw our eclipse hydrogens here. Well, it's the same exact thing as our staggered. Our carbon could be here, our carbon could be here, or our carbon could be here. Now, let's see that out. See? Our eclipse version. Don't forget the hydrogens on that carbon too. I didn't draw it just for the sake of space. Let's see. Carbon there, carbon there, carbon there. And that is our potential energy for propane. Pretty cool, right? Yeah. I know you guys are clapping for me. I know, I just know it. That is my wonderful explanation. I hope you guys loved it.